Good morning, my name is Victor, and today I'm going to talk about the main topic I work in my group, GAP, which is called Entanglement Dynamics or Primality Identification, a quantum approach. So, there are many reasons prime numbers are important, and we all know they come from ancient mathematicians, but today we find them to be present in computing theory, like in cryptography, but also in sciences like physics as well, and biology. And we know prime numbers are in a way the building blocks of integers, and we find their distribution to this day still mysterious. In fact, we have the bottom left image for the Riemann function, which has a conjecture still unproven today, but if true, will change our understanding of the distribution of prime numbers. So, a really important topic in mathematics in general. And when we talk about the identification of this type of integers, we are talking about efficiency, which is what we are concerned here in this work. So to summarize how classical algorithms and quantum algorithms in this aspect, this type of problem work, we could say that they work classical ones mainly using mathematical theorems, number theory results, and for example, the Sieve of Eratosthenes, which is the closest algorithm that does the same as mine does, which I'm going to present. And when we talk about quantum computing, we have quantum physics behind, and phenomena like quantum interference and entanglement are what differentiate it from classical methods. And in general, we have methods specific for certain types of integers to try to identify prime numbers. And in general, they are slow. And quantum computing as a promising alternative to classical computing show potential advantage. And the way they approach this usually classically is to eliminate composite numbers to find the prime numbers, while as well in my work, we focus on finding the primes themselves. So the idea started in this work of 2023, identifying prime numbers for entanglement dynamics from researchers of Santos. And the idea they proposed was pretty simple in a way, but very specific. So we have a quantum system, and we developed its entanglement dynamics, and we studied the statistics by measurement, and we find that for a certain type of system, in the case of this paper, it was a quantum harmonic oscillator. We find that after a first series analysis, there is classification of prime numbers within this Fourier analysis of the entanglements. And in the following year, we went a bit further. We generalized this idea. They only developed the theory behind, and we as well the big result was to develop a quantum computing algorithm, which is something they didn't do in their work. So we published physical way on this topic. So going a bit specifically how we do that in theory. So as I said, we start with a quantum system. In this case, it is a two-part system, A and B. And as I said, they started with originally with a quantum harmonic oscillator. So the important part is that the energies must be proportional to some integer. So the NS energy level must be mathematically equal to the constant times the DNS integer. So there are some details like we facilitate to get product states of the two parts of the system. We go to dynamics, which we know from standard quantum mechanics, since the Hamiltonian is already written in its eigenbasis, the evolution operator U will be written like that as well. And this is results that we have shown. I'll get more specific to specifics soon, but we have shown big results that the U we need to use here, this one, is uses a small number of gates when computing, which is surprising for this type of unitary gate, which is diagonal matrix form. So after that, we go to Entanglement Institute, and we find that the entanglement function has this form, and this decomposition is what we are concerned. So finally, we reach the part where we identify the prime numbers themselves, and I don't know if you can see it, but there are the amplitudes for the states, C. But the important part is that we have this delta in the other index is minus k times 1 and this is in some way the decomposition of n into products of true integers. So of course n can always be decomposed as n times 1, but when n is composite number, there are other decompositions. For example, if it is a even number, it can be decomposed as n divided by 2 times 2. So there are many other decompositions for composite numbers, but they all share this trivial one, which is of course the decomposition for prime numbers. So the great result is that we get this inequality, which means the Bn is the lower bound, which is the result for the trivial decomposition. And this inequality is only an inequality when n is a prime number, and when n is a composite number, it's always bigger than Bn. Now, this is the theory. Now we go to the quantum algorithm, which concerns the quantum computing part. So we have two systems of d dimensions, and we translate that into many qubits. This is the trivial part. The complicated part is to create a circuit that does all these dynamics efficiently. And I'm not going into details, but this part is where we prepare the initial state, which is easy since we can choose any initial state. This is the great result I talked about before, the preparation of the evolution operator, which should be efficient, but in this case we have shown theoretically that it is efficiently implemented. And this part is where we measure the entanglement function. So after we do this for a whole period, to go to the integration, we go to post-processing, and we use here we found out that Simpson's method is the best one for this type of problem. And as I said, we take this for a whole period. We use the statistics to obtain the Fourier modes through integration, numerical integration. And here I brought just one value of t for the simulations. We did many more. But as I said, this is the entanglement function, which is not really relevant, but since it's simulation, it's good to compare how good it is to the analytical value. But here is the result we are concerned. So points in red are the analytical, in blue are the simulation. And as I said, the n values that are on the green lines are respectively the prime numbers, and all of them that are above are the composite numbers. So these are the parameters we use. P is the number of partitions, we did for the integration. And when we did that for many values of u, we found out the number of gates scales with t squared for the quantum circuits. So what we are doing now, and in the dome I'm showing here, we are doing experiments. And these are all simulations, but there are experiments that we are doing right now and going to do more in the future. And there are some challenges that quantum computing face today. I'm not going into details, but here I just brought which is supercomputing, quantum computing. The points in red are the qubits, and you see for example, this one has only access to its neighbor qubits, so it's a limitation. If I need to apply some operation between this and this, I have to swap the states of them to do that, and this creates noise, which complicates the results, gives bad results. And here is a trapped ion on the computer, which is a good alternative. It is not necessarily the best, but it has this auto-open activity that I said that this one may access the other ones, but it's lower, so it has its advantages, but also its disadvantages. And that's pretty much it. Thank you.